All right, now let's look at boundary and initial conditions. Okay, we'll start with boundary conditions. Okay, well, all physical problems have some sort of boundary. Okay, so all physical problems will have some sort of boundary conditions. Now, they can vary quite a bit, and some can be very complex, but nonetheless, they will all have such a thing if we're trying to model something. And now, in the case of our particular heat flow problem, the boundary conditions are pretty straightforward. Okay, so let's do that. We're pretty straightforward. And whoops, straightforward. There we go. F-O-R-W-A-R-D. Okay. They're just, at each end we had these constant temperatures. So so we have U of 0 and, oops, sorry, forgot my X there. Or no, I needed a T, never mind. I didn't forget that. Okay, 0 T. So for all time, this is a constant temperature of T1. And at the other end, for all time, it was a constant temperature of T2. And so to do all time, we just put in here greater than 0, T is greater than 0, but less than infinity. Okay, so there are the boundary conditions in our case. They're pretty straightforward. Now, initial conditions. Okay, well, again, all physical problems start somewhere. Okay, so we'll have to take that into account, and again, our problem is pretty straightforward. So in this case, we start with the rod, everything's at temperature T0, so I would write that as U of X at time 0 is just T0. And that's for all the X that we care about, so that's the length of the rod. And so we have that for our initial conditions. And so what that gives us, this yields the complete model Okay, so we have our model of the heat flow, which is U sub T is equal to alpha squared U sub XX 0 is less than x is less than L, so along the rod, and again for all our time. Now notice these are strict inequalities because our boundary conditions and initial conditions will take care of the inequalities at each end of the rod, so the 0 and the L, and at the beginning of time, t equals 0. So we put in our boundary conditions. So u of 0 and t is t1, and u of L and t is t2. And that, of course, is for 0 less than or equal to t less than infinity. So you see we've taken care of the case where x equals 0 and x equals L. And then our initial condition takes care of the case where t equals 0. We have u of x 0 is equal to t0, and that's 0 is less than or equal to x is less than or equal to L. So there's a complete model right there. Now, and though we don't prove it here, we know it has a unique solution. Okay, so, our time would be to find, our time would be spent trying to find what that unique solution is. But that takes care of our boundary and initial conditions, which then gives us this complete model statement here where we give the PDE as far as how we model the flow itself, but then we also give you the boundary conditions and the initial conditions, which are needed to actually solve the problem. So there we go.